Engineers just designed an airplane that uses 20% less fuel than anything flying today. It passed its flight tests. KLM backed it. Airbus took notice. On paper, this aircraft could save the airline industry billions of dollars a year and slash carbon emissions at the same time. There is just one problem that nobody is talking about. They have no way to load cargo onto it. Every time you buy a cheap plane ticket, you are being quietly subsidized by cardboard boxes, not metaphorically. Airlines earn somewhere around $40 to $50 billion every single year from freight stuffed into the belly holds of passenger planes. On many long-haul routes, that cargo revenue is the difference between a profitable flight and a money-losing one. The containers that carry this freight are called LD3s, and they are the universal language of air cargo. Every wide-body airport on Earth, every warehouse, every loading vehicle, and every gate is purpose-built to move these containers on and off cylindrical aircraft fuselages. It is a system so standardized that an LD3 packed in Shanghai slides seamlessly into a hold in Chicago without a single adapter. And a radical new aircraft design is about to shatter that entire system. The Flying V started as a thesis project. A student named Justus Beynard at Airbus Hamburg sketched an airplane where the passenger cabin, cargo hold, and fuel tanks were all integrated directly into the wings, forming a dramatic V shape. Researchers at Delft University of Technology picked it up, and KLM Royal Dutch Airlines funded further development. The idea was simple but audacious. Instead of bolting wings onto a tube, you make the entire aircraft one giant lifting surface. The result burns 20% less fuel than an Airbus A350 while carrying the same number of passengers, 314, and the same cargo volume, 160 cubic meters. In the summer of 2020, a scaled model completed a successful maiden flight. Investors started paying attention. JetZero, a California startup working on a similar blended wing-body concept, landed a $235 million contract from the US Air Force to build a full-scale demonstrator. NASA and Boeing have been testing their own versions for years, and here is the detail that made cargo executives relax. The internal hold of the Flying V was specifically engineered to accept standard LD3 containers. Same containers, same cargo, same revenue, no problem. Except there is a massive problem, and it has nothing to do with what is inside the airplane. Picture a normal wide-body jet parked at a gate. The fuselage is a cylinder. The cargo doors sit on a flat vertical surface along the lower fuselage, well clear of the wings. A standard high-lift loader, essentially a platform on wheels, drives straight up to the door, sits flush against the fuselage, and slides containers in and out. It is a process repeated tens of thousands of times a day at airports around the world. And it works because the geometry is simple. A flat loader meets a flat surface at a right angle. Now picture the Flying V. There is no cylinder. The fuselage and wings are fused into a single swept triangular shape. The cargo doors do not sit on a flat vertical wall. They are positioned along sharply swept surfaces where the body tapers backward at extreme angles. A standard loader, which is a perfect rectangle designed to sit flush against a straight tube, cannot form a seal against a surface swept back at such a steep angle. The result is massive, dangerous gaps between the loader deck and the aircraft door, gaps where workers and cargo could fall. Engineers confirmed the LD3 fits inside, but they did not solve how the LD3 gets inside. And this is not a minor inconvenience that a cleverly redesigned ramp can fix. The entire global fleet of cargo loading equipment, tens of thousands of machines at more than 4,000 airports, is engineered for one shape: a tube. Every high-lift loader, every belt conveyor, every container dolly system assumes the cargo door is on a flat section of a cylindrical fuselage, perpendicular to the ground, with clear lateral access. The Flying V violates every single one of those assumptions simultaneously, so the aircraft can hold the standard containers. It just physically cannot receive them using any equipment that currently exists. And if you think this sounds like a solvable engineering puzzle, consider what happened the last time the industry tried to accommodate a non-standard aircraft. When Airbus launched the A380, airports around the world spent hundreds of millions of dollars widening taxiways, reinforcing runways, and building custom double-deck boarding bridges. Entire terminals were redesigned. And that was for an airplane that was still fundamentally a tube with wings, just a bigger tube. The A380 kept the same basic fuselage geometry, the same cargo door orientation, the same loading equipment compatibility. Airports still had to pour fortunes into accommodating it, and when Airbus cancelled the program, much of that investment was left serving a plane that no longer had a future. The Flying V is not a bigger tube, it is the elimination of the tube entirely. The infrastructure challenge it presents is not about the raw cost of a single loader, it is about the death of standardization. Today, a cargo loader in Shanghai is identical to a cargo loader in Chicago. The Flying V destroys that universality, and replacing it means designing, certifying, manufacturing, and deploying an entirely new class of equipment while simultaneously maintaining the old fleet for every conventional aircraft still flying. That dual fleet logistics nightmare is where the story stops being about one experimental airplane and becomes about a systemic collision between the future of flight and the reality of the ground. The air cargo industry is not in a position to wait. IATA Director General Willie Walsh said in March 2026 that freighter manufacturing supply chains remain unstable years after COVID, and the average age of the global cargo fleet is, in his words, significantly higher than the passenger fleet, with the gap widening. Airlines are desperate for new, efficient capacity. Conversion feedstock from retired passenger jets has dried up because those passenger jets are not being retired. They are still flying because new aircraft deliveries are years behind schedule. The industry needs next-generation airframes. Blended wing bodies and Flying V-type designs promise fuel savings of 20 to 30%, which would fundamentally reshape cargo economics and open secondary routes that are currently commercially unviable. The technology is ready. The aerodynamics work. The fuel math is spectacular, but none of it matters if you cannot load a single container at the gate. This creates what economists call a coordination failure, and it might be the single greatest obstacle to the biggest aerodynamic leap in 60 years. Airlines will not order Flying V or blended wing aircraft until airports can service them. Airports will not spend billions redesigning gates, purchasing custom loaders, and retraining ground crews until airlines commit to large orders. And no equipment manufacturer will develop and mass-produce an entirely new generation of cargo loading vehicles without confirmed purchase volume from airports. Three parties, each waiting for the other two to move first. Meanwhile, the clock is ticking. Aviation's carbon targets demand radical efficiency gains within the next 15 years, and conventional tube and wing designs are approaching their thermodynamic ceiling. The 20% fuel saving the Flying V offers is not a luxury. It is precisely the magnitude of improvement the industry says it needs to meet 2050 emissions goals. And every year, this coordination failure delays adoption is a year those savings do not materialize. Now consider the scale of the logistics challenge. Equipping a single major hub with a parallel fleet of custom loaders for V-shaped aircraft, while keeping the existing fleet running for every conventional plane, creates a logistical and operational burden that multiplies across every airport these aircraft would serve. Someone has to pay for it, and right now, nobody has agreed to. Airlines say it is an airport infrastructure problem. Airports say they will not invest without airline commitments. Governments have not yet grasped that the ground, not the sky, is the actual bottleneck to next-generation aviation. Here is what makes this truly unsettling. The Flying V team at Delft spent years optimizing cabin layouts, fuel integration, aerodynamic profiles, and structural loads. They ran wind tunnel tests, computational simulations, and a real flight demonstration. They have even published research specifically addressing ground servicing and turnaround compatibility, with detailed diagrams showing how cargo loaders, catering trucks, and jet bridges could theoretically interface with the aircraft. But finding a theoretical fix on paper is a completely different problem from mass-producing custom loaders and deploying them to 4,000 airports worldwide. The most mundane part of aviation, the 15 minutes a plane spends being loaded at a gate, could quietly kill the most important aircraft redesign in half a century. And the cargo industry, stretched thin, fleet aging, supply chains fragile, cannot afford for it to fail, but also cannot afford to be the one holding the bill. The planes are ready, the sky is ready, the ground is not. And until someone figures out who pays to redesign 4,000 airports, the most fuel-efficient aircraft ever conceived may never carry a single box. If that tension between revolutionary engineering and stubborn infrastructure surprises you, wait until you see the story behind why the world's largest airplane was never allowed to carry cargo. That one is right here.